In the realm of HVAC systems, selecting the correct chilled water pump is crucial. Let's delve into vital tips for choosing the optimal pump and the significance of thorough testing and commissioning processes. The first thing I must say is that more pressure does not mean more flow. I get calls from clients all the time saying they aren't getting adequate cooling from a chiller, but there's great pressure, so the problem isn't the flow. I take a deep breath, bite my lip, and then proceed to talk about pump performance curves and give them a simple analogy. If you have a garden hose and squeeze the end of the hose, the pressure builds up in the hose and you squeeze it, higher pressure before the point of the squeeze, but you are reducing the flow rate coming out of the hose. The velocity speed of the water coming out will increase as you are forcing the water through a smaller area, but let's just stick flow and pressure for now. So if you have a restriction in your pipework, such as a water strainer blockage, the pressure upstream to the blockage will show an increase in pressure, but the flow rate will be reduced. Let me explain this from the start. When sizing a pump for a chilled water or hot water hydronic circuit, we need to consider the required flow rate first, then the pressure required. Assuming you have the cooling or heating capacity and the delta T, the flow rate is determined by the engineer's favorite formula, Q as MC, Q equals sign capacity, M equals sign mass flow rate, C equals sign specific heat capacity, D equals sign delta T, temperature difference. I'm not going to even complicate this by giving you units of measurement for each. Example. Let's say we have a chiller that is 100 kW with a flow temperature of 7 C and return temp of 12 C, DT at 5 C. We can rearrange the formula, and this will equate to flow rate of 20 EM3H. You can get pumps that will deliver the same flow rate, but at completely different pressures, so it's important that you know what pressure you actually require. As you can see from the sample pump curve below, there are various pump options with the same flow rate, but with different pressures. Therefore, we need to know what are the total maximum pressure drops in the chilled water system. If there are multiple circuits in parallel, you must take the circuit with the highest pressure drop. So, let's say the pressure drop is 2 bar. If the pump is integral to the chiller, this pump must deliver the flow rate of 20 M3H with an available pressure of 2 bar, after allowing for the pressure drops within the chiller. It is preferable to select a pump with the above performance mid-curve. In the sample pump curve attached, you can see the Lowara CEA 370/3 is perfect for this design criteria. If the pump is to be located external to the chiller, and the chiller has a 0.5 bars pressure drop on top of the 2 bar pressure drop in the circuit, you will need a pump that will deliver the flow rate of 20 M3H at 2.5 bars. Of course, the system design may have a primary loop and a secondary loop, but you still use the above for each circuit, with the exception that the flow will be divided up amongst the various circuits. Beware that the pressure you read coming off a pump may not be the actual pressure being delivered from the pump, as with all sealed and pressurized systems. You will have a static pressure in the system, so you should deduct the static pressure from the pressurization unit from the pump pressure to get the actual pressure being delivered. Needless to say, the pressure will drop as you follow the pipework around the circuit and back to the pump. Understanding the intricate details of HVAC pump selection ensures optimal performance and efficiency. Delve into the world of chilled water pumps where precision meets functionality. Remember, the heartbeat of your HVAC system lies in the choice you make. Stay informed, stay ahead.